Okay, so before we do this problem, I'm going to go back to 6.2 and a uniform distribution. We get so involved in a normal distribution and z-scores and everything, we forget about what is a uniform distribution. So one of the examples that we had in our book was the waiting times for a subway. So the total under the curve under any distribution still has to be equal to 1. And this particular one says that every point on the curve has the vertical height, which has to be greater than 0, which is true. And it is a uniform distribution of the time in New York City in late afternoon to travel. And how many minutes you have to wait for the subway. So, and it says it's uniformly distributed between 0 and 5. So 0, 1, 2, 3, 4, 5. 5 minutes. And it's evenly distributed. So that meaning, of course, that my distribution of wait times looks exactly like that. Looks like a rectangle, which it is a rectangle. So how do I know what this is on this y-axis? Is I have to do the math. So I have how many? 1, 2, 3, 4, 5, correct? And what do I do? What is my area under here has to be? What? Area has to equal 1. So if I've got one side of my rectangle being 5, what do I multiply 5 by? So when I get this length of this side here, 0.20. 0.20. Because 0.20 times 5 gives me back 1. Or length times width equals the area. Or I could have said 1 divided by 5, and if you do 1, the area of 1 divided by 5, what am I going to get? 0.20. So regardless, this area has to be 1. That's how I know what this wait time has to be. Okay? Has to be. So then if I said, what is the probability that I'm going to wait for 3 or more minutes? 3 or more minutes. Well, I'm going to do it just like I did on the normal curve. I'm going to say 3 minutes right there, right? Or more, where am I shading? To the right. So this is the area I'm looking for. But we don't need a chart for this area because it's simply a rectangle, correct? So to find the area here, I've got 1, 2 times what? 0.2. So 2 times 0.2. And that's going to be my probability of waiting 3 or more minutes. It's going to be what? 0.4, 40%. Is that better? Uniform distribution. Uniform distribution. 6.1 is really just a little like introduction to what's coming. Yeah, 6.2 is where you found your uniform distribution and the normal standard distribution. You looked at reading the table and things like that. Because my whole area of this entire rectangle has to still be 1. And if I know the length of this side of the rectangle, 1, 2, 3, 4, 5, I'm going to take the area, divide by 5, and get 0.2. Because 5 times 0.2 gives me the area of 1, length times width. Okay? Three minutes or greater. Now, this is my scale of how many minutes. So just like I would in a normal distribution, I'm going to find my point, then I'm going to shade. And what am I shading? I'm shading the area that I need to find under the curve. This is what I had to do here, is shade the area under the curve that I needed to find. So it's 3 minutes or more. So I'll have 3 or more. So it could be 3 minutes, 4 minutes, or 5 minutes. So I really want to find this area. Well, what is the area? It goes from, I need another color here. It's 1, 2 units long there, right? And how high is it? Well, the height is always going to be 0.2. So length times width will give me that area of that smaller rectangle. Okay?
So if it was 1, it would be just 0.1?
Yes. If I said, looking at that distribution, what is the probability that I'm going to wait 1 minute? 0.2. Yeah, depending upon which one. If it's just one, if I'm just saying only 2 minutes, not 2 or less, but just 2 minutes, it'll still be 0.2. So 0, I have a 20% chance of waiting, not waiting. If for 1 minute, I have a 20% chance that I'd wait 1 minute. I have a 20% chance I'd wait 2 minutes. I'd have a 20% chance I'd do 3. Now, because it's just that minutes, that because it's uniform. Regardless, okay, I've got a 20% probability of waiting 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes. Okay? The difference becomes when I said here, I said, what's the probability of waiting 3 or more minutes? So what's the probability of doing that? Then I have to say, okay, what's my area? Okay? Uniform distribution. Clear as mud, right? Okay. And Kimberly, you had some that you want me to do. It was a 6.4 one, okay. And I've got some problems that I already have so that I can do 6.5 practice. Okay. Okay, this is for the distributions, correct? We talked about this one too, Jemiah. I remember that. That was so annoying.
I'm sorry. It wasn't annoying. It was just like, I don't understand the purpose of it. Why are we finding it? It makes me question, if the number's odd, you have a higher chance of picking an odd number. Is that what they're trying to say? Because at the end of the day, no matter if the number's odd or if it's even, you have the same opportunity of picking it. So that's where I was confused with.
Okay, so let's go over this problem. This happens to be, I guess, problem number 1 out of 6.4. 3 randomly selected households are surveyed. The number of people in the households are 4, 5, and 9. Assume sample size of n equals 2. Okay? Are randomly selected with replacement from that population of 4, 5, and 9. First, construct a probability distribution table that describes the sampling distribution of the proportion of even numbers when samples of n equals 2 are randomly selected. Does the mean of the sample proportion equal the proportion of even numbers in the population? Do the sample proportions target the value of the population proportion? Does the sample proportion make a good estimator of the population proportion? And they even give you the 9 possible samples. Well, on your test, I may give you a problem, but I won't give you the 9 possible samples. You would have to figure them out. And we did that, I think, on Wednesday, right? So always remember that we're with replacement. So my possibility of taking a sample of 2, given I have 4, 5, and 9, I could do a 4 and a 4, correct? I could do a 4 and a 5. I could do a 4, then a 9. Yes? Now I'm going to do everything when I start and I draw 5 first. So I could have a 5 and a 4, and a 5 and a 5, and a 5 and a 9, correct? Then I'm going to go through selecting 9 first. So then I have a 9 and a 4, and a 9 and a 5, and a 9 and a 9. Those are my possible ways to get a sample of 2 from those households with 4, 5, and 9 people. I think what confused us on this one was when the sample I did on the board, we got the sample mean. We got the sample mean. So the sample mean would be 4, this one would be 4.5. That's the problem that we did. But that's not what this problem is asking. This problem is the proportion of odd numbers on the proportion of even numbers. So some of you may have had odds and some of you may have had evens. So if I look at 4 and 4, those are even numbers, aren't they? So what's the probability there that I picked an odd number? 0. So my next sample is 4, 5. What's the probability of the odd number there? 1/2. How about 4, 9? 1/2, right? How about 5 and 4? 1/2. 5 and 5? 1. 5 and 9? And again, 1 and again, 1. And I think that's what the confusing part was. It had to be that you were not finding the mean, you were finding the probability of having an odd number. I think that's what the confusing part was. So then they looked at, well, what is the probability then of the whole thing that I would choose and I would have 0? Well, one out of 9. So the probability of 0 would be 1 out of 9. How about of a half? 1, 2, 3, 4 out of 9. And how about 1? Okay. Is that better? Okay. Okay. Good. Good. All right. So, I don't remember which problem I put on there. I know there's a problem on there, but I don't remember which type. Okay. Okay, so these are some problems that I had used at another time for practice, for working with Chapter 6. So I think it's just a good idea to go ahead and look at these, especially when I see some questions coming up. Number 15, water safety, water taxi safety. Passengers died, this is for real, when a water taxi sank in the Baltimore's Inner Harbor. And a water taxi, you can go to they still have them at the Inner Harbor. literally you go, you get on the little water taxi, which was what, a boat, and they take you to different areas of drop off in the harbor. Um, so it says men are typically heavier than women and children. So when loading a water taxi, assume the worst case scenario. So the worst case scenario is going to be they are all men. And assume that weights of men are normally distributed with a mean of 182.9 pounds and a standard deviation of 40.8 pounds. The water taxi that sank had stated a capacity of 25 passengers, and the boat was rated for a load limit of 3,500 pounds. So, given that the water taxi that sank was rated as such, what is the mean weight of the passengers if the boat is filled to the stated capacity of 25 pounds? 140 pounds per person. And you got that by?
Well, there's a total limit of 3,500, and you're putting 25 people on there, so you have to divide the 3,500 by 25, and that gives you your 140 pounds per person.
Perfect. So let me just change color here. Let's say the reason what he did was take 3,500 and divide that by 25. So they're assuming then that was 140 pounds each person. That was the assumption for this mean of the weight of passengers. Okay. Part B, if the water taxi is filled with 25 randomly selected men, what is the probability that their mean weight exceeds the value from Part A? 100%. Let's see, let's find out. What am I going to use? I'm going to use the normal distribution. Yes, because this is what they were basing it on, correct? That I can have a capacity of 25 passengers, but my load limit being 3,500 pounds. So that means they based it on 3,500 divided by 25, that each passenger would weigh 140 pounds. So Part B then says, well, if the water taxi is filled with 25 randomly selected men, what is the probability that their mean weight of the men that's on there exceeds the value that you got in Part A? So let's first draw our curve. We know that it's 182.9. And the standard deviation is 8 pounds. Okay. And we could fill out the chart. We could go down by 40.8 and up by 40.8 and fill all that out if we wanted to. And the mean that they came up with was 140 pounds, correct? Based upon their numbers, 3,500 pounds and 25 passengers. So if that's the case, 140, we'll just take a look at 140. If I subtract 40.8 from here, I'm going to end up with 142.1, correct? I'm still not even down there, right? I'd have to go a little bit further. So taking that into consideration, I'm going to say, oh, it's probably right about there. So now that I have my sketch, let's go back and read what it says. What is the probability that their mean weight exceeds the value of Part A? So what am I shading in my curve? Exceeds is to the right, gets bigger than. Is it that or larger? So it gets, so this is my shading. This is the area under the curve. Hmm.
Now, are we gonna have to use I forgot the proper name for it, like the mass distribution thing, like to make it more, because it says, we're doing 25, or we can just, this be considered for just one person?
Well, this one is 25 randomly selected men.
So we need to change the distribution?
Okay, so let's read part C then. After the water taxi sank, the weight assumption revised, blah, 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 blah. So, is the new capacity of 20 passengers safe? So I'm not selecting one.
Yeah.
I'm selecting what?
All 20,
All 25.
we need to change the distribution.
So you have to change the standard deviation. Why? What's that thing called? Central limit theorem. Central limit theorem. So, how am I going to change that? You guys tell me.
5, divided by square root 120.
Up, backwards. So my new one is going to be
1.8, right? Divided by square root 2.
and what are we going to get for that? 8.16? So with those new numbers, you can put it in the calculator. But let's think about where I'm going to really be. I'm going to be way down here, aren't I?
That makes more sense.
That makes more sense. It does.
It makes sense that it's 100%, but then not the whole area was shaded in. So
Right.
it's a single percent still area left.
Yes.
But now with it moved all the way down there, it's too much dumping that's left.
That's right.
Now, are you shading it like that because we had a new standard deviation?
Yes. Absolutely.
If it was 40, it needs-
Right.
Okay.
It
Correct.
would only been a little over one standard deviation to the left before. Now it's like way down.
Because the standard deviation, because I'm doing 25. Excellent. Okay, and I did not start my calculator, so let me pull that up. Mm-hmm. Okay, so given those numbers, who can recall, what do we do on the calculator? What are we looking for?
The percentage.
We're looking for the area, aren't we? The probability. So I'm going to go to second, distribution, the second one, the normal curve. Okay, I'm going to press enter, then I'm going to fill it out. I got to tell it my lower level and my upper level.
The lowest and 40.
The lowest, and I'm going to use the actual numbers, the actual data instead of the standardized. So my lowest is 140. Not, oh, I always do that. Cancel. Okay, what's my upper limit going to be? 99999. I went all the way up to the right, right? Then mu is 182.9, and my standard deviation is, and I'm going to get, I think we could round that to say 100%. So when I go back here, it's 100% chance it will exceed my weight limit if I have 25 passengers. Would you want to get on that taxi? Not I. If you can swim, you're good, right? So after the water taxi sank, the weight assumptions were revised so that the new capacity became 20 passengers. If the water taxi is filled with 20 randomly selected men, what is the probability that their mean weight exceeds 175 pounds, which is the maximum mean weight that does not cause the total load to exceed 3,500. What did they do? They took 3,500 and divided by 20, and they got 175. Okay? So they revised it to say 175. So let's find that. We can go back to our calculator. What am I going to put as my lowest limit?
Don't you have to change that, the population standard deviation? Because you're only using 20 now instead of 25 passengers.
Mm-hmm.
So you have to divide the,
We have to divide
0.8
by square root of 20.
which gives you, 9.12 now.
That's going to be 9.12. Good. So if I do 40.8 divided by the square root of 20, and you said it's 9.12? Okay. And my lower limit's going to be what? 175. Isn't that my new weight standard? My upper limit's going to be still the 99999. Standard deviation is 9.12. I came up with 0.8068. Still not good, is it? Better. Better. Still not good. So we'd start counting before we got on, right? So 0.8068. So there's still almost an 81% chance that I would exceed if I had all men on there, and there were 20 of them. So is it safe? No. Yeah. So now when you read those elevator signs and you get in the elevator, it'll say how many capacity of people and total pounds. Are you going to start doing your division in your head? Go, ooh. Right? If it was less than 5%, yeah. Because why? Because this is pulling out and based upon what? The worst case scenario, which would be that they were all men. More than likely, it's not going to be all men that get on a water taxi, right? But we want to err on the side of caution, meaning that the worst case scenario.
We all 19-year-old men that they could be
And, probably if you're sightseeing, it could be couples, it could be a family with 2 kids, so that likelihood of it being all men is small. Yep. Good. Good. I think we did this one. I know we did that one, didn't we? Yeah. Okay. Number 14 is on designing manholes according to the new website. Manhole covers must be a minimum of 22 inches in diameter, but can be as much as 60 inches in diameter. Assume that a manhole is constructed to have a circular opening with a diameter of 22 inches. Men have shoulder breadths that are normally distributed with a mean of 18.2 inches and a standard deviation of 1 inch. What percentage of men will fit into the manhole is part A. Part B, assume that Connecticut Light and Power Company employs 36 men who work in manholes. If 36 men are randomly selected, what is the probability that their mean shoulder breadth is less than 18.5 inches? Does this result suggest that money can be saved by making smaller manholes with a diameter of 18.5 inches? Why or why not? So I'm going to pause this right here. Okay. Um, part A. Part A. I'm just looking at the whole population, the diameter of those manholes, the mean being 18.2 inches with a standard deviation of 1 inch. So I want to know the percentage of men that will fit into a manhole. And it's a manhole of 22 inches in diameter. So when I get my 22 inches, I'm going to be up here a little ways, aren't I? What side am I shading? Am I shading to the right or to the left? I want to find the percentage of men who will fit in that manhole. The manhole is 22 inches. I got to go to the left. Why?
And 22 or less.
Yeah, because if I have a man up here who has 23-inch breadth, is he going to fit in a 22-inch diameter manhole? No. I want to know those that will fit. That means 22 inches or less. So I want this area. Again, you can use your table, you can do the z-scores, you can go ahead and use your calculator. So I'm going to go second distribution again, and I'm going to go down to the normal curve. My lower limit is going to be what? Negative 99999. My upper limit is going to be 22. The mean is going to be 18.2. Standard deviation is 1, yes. So looks like 99.99, I'd say 100%. Pretty darn close, 100% of men will fit in that. Okay. So we're now on part B, and assuming that the Connecticut Light and Power Company employs 36 men, so it's a sample of 36 men who work in manholes. If the 36 are randomly selected, what's the probability that their mean shoulder breadth is less than 18.5? So now, the mean is still 18.2, but my standard deviation is going to change because now I have a randomly, right, and I'm going to end up taking 1 divided by the square root of 36, or 1/6, which is going to be
Wait, I'm confused. Why 1? And I thought it would be 18.5.
that, not the mean divided by, it's the standard deviation divided by the square root of n. Okay? So now my standard deviation is much smaller, and I want to know at 18.5, so if I go up to 18.5, it's going to be somewhere in the right-hand side, correct? And again, I'm not drawing the scale, I'm just guessing. What area am I shading? It says, what is the probability that their mean shoulder width is less? It's less than, whoops, I meant to make that highlighter, sorry. So I am going to shade to the left. So I want this area And again, I'm going to use my second distribution and go to the normal curve. I'm again going to have that lower limit as being negative 99999. My upper limit is going to be 18.5. And mu is 18.2, but my standard deviation now is 0.167. And I find the result to be 36%, or 36, sorry, 96%, 96.37. I got 0.9637. So 0.96 rounded. 637. I think that rounds to an 8 though. What did I use in there? No problem. What, 0.167? So that was negative 99999. The upper is being 18.5. My mean stayed the same at 18.2. Oh. Yeah, it's going to be just a little piece difference. Round to the third. 0.167 in this case. Yep. No problem. Okay. So given that result, does it suggest that we should save money by making those smaller? Why or why not?
There's still a percentage.
Yeah.
But it can happen.
Right.
And if it does happen, then you're stuck with somebody who's not able to enter any manhole anywhere.
Exactly.
It's limited for his capabilities of doing his job.
Yes. What we found in part A was that almost 100% of men would fit in a 22-inch diameter hole. This one, we found just a random sample of 36 would be a 96% of those samples. So if I went back here and said, hey, if I change this to 18.5, am I reducing a lot of our population? Yeah, because this result is based on a random sample. This is the entire population. Does that make sense? So I wouldn't want to change those manholes. Okay. Plug it in. Plug it in. I'm seeing some, like, I have no clue what she just said. Second distribution. So our upper limit is going to stay 18.5. Our mu is 18.2. But now I just want the entire population. So I go back to my standard deviation of being 1. Because now I just want to look at, should I make those longer, smaller or not? Not based on the 36 that's a random sample. Instead, the whole population. What percent of my population would fit in a manhole of 18.5? So when I did that, it's only 61%, 62%. So I'd be cutting down a lot of the population.
This might be a silly question. Something that just clicked in my mind. So the standard deviation, is it basically how many people it is or something?
Standard deviation is, again, the spread. It's a measure of spread from the mean. How many people, how far apart they are. So
It couldn't be, someone says like 14.1, you can have a, if it's small, so that's 1 from the first.
right,
So that's why.
it's the spread. It's the measurement of the spread of the data. Okay.
So it's not like unusual when it comes to the entire population.
Correct.
With that random sample of those specific 36 people that work for that company,
Yes.
it would be unusual, but not for the entire population.
Correct. Because I would be losing a big percentage of the population that would fit. Right. Correct. correct. Good.
The first part, the same question, include the lower limit is still negative 999.
Yes. 18.5, because the question was, should I make my manholes now only 18.5 instead of making them full 22? Well, I wanted to look at the population, the entire population, what percentage of men would be 18.5 or less. And then we found it only to be 61%. That's why I went back to using standard deviation of 1, because I wanted to look at the entire population, not just a sample. Okay. I think that's the last one.